Hello, everybody, and welcome to the first video lecture for Math 4400. So this is just really an introduction to the course, so it's an introduction to an introduction to number theory. Somehow I just want to give an overview of what is the topic of number theory, like what a number theorist is interested in, and say a little bit about the things we'll talk about over the course of the class. So I'll mention some things that sort of are just for context, aren't going to come up again, and I'll mention some things that we'll come back to, and I'll try and sort of specify what's what. But everything today is just sort of supposed to be an example, an illustration of some ideas, and it's not stuff you're expected sort of to take all in right now, or even necessarily over the course of the entire class. So this is just sort of a panorama or sort of impressionist painting of what the class is going to be. Okay, so the question I want to answer then today is just, what is number theory? Okay, so to answer that, well, the first thing we better answer is sort of, what are numbers? So you can imagine that we're a bunch of, well, my ancestors were a bunch of monkeys living in trees, probably yours too. And well, they were sort of concerned with very practical things like how many bananas they had. And they started to realize it was useful if they could keep track of exactly how many bananas they had. And they introduced the counting numbers, natural numbers, like 1 banana, 2 banana, 3 bananas, 4 bananas, 5 bananas for the monkeys that are doing really well. And so they started keeping track of things that way. And then one day, my monkey great-great-great-great-great-great-great-great-great-great-great-great-grandfather and grandmother both realized, hey, we're out of bananas. We don't have any bananas. They sort of invented the number 0 to express that concept. And that ended up being a pretty important idea. The idea that not only can you have some of something, not only can you have 2 bananas, you can have no bananas. You can have 0 bananas. 0 is quite a useful number. And sort of that kind of thinking sort of led to sort of negative numbers as well. So one day, sort of a monkey was out there and he was holding 3 bananas. So he's like, okay, I'm doing pretty good. I'm holding 3 bananas. But then he remembered sort of, he has 5 friends and he sort of borrowed a banana from each of them. So he had 5 friends and he borrowed 1 banana from each of them. So he needs, actually sort of, he's in the hole 5 times 1, which is 5 bananas. So even though he has 3 bananas, he owes out 5 of them. So actually he sort of has minus 2 bananas. So somehow, once you started doing monkey accounting, you needed negative numbers. And sort of that brought us to the integers, which is sort of the fundamental building blocks of number theory. So it was sort of somehow, in number theory, we talk about lots of other things, but the integers and sort of inside of that, the natural numbers, like those are sort of always our touchstone for things we're trying to understand. Okay, but then sort of the monkeys introduced envy, and that sort of one monkey was holding 2 bananas and another monkey was holding 3 bananas, and was trying to quantify how jealous that monkey, the first monkey was trying to quantify how jealous they were of the second monkey, and they realized the second monkey had sort of 3 halves as many bananas. And sort of to express that ratio, 3 bananas to 2 bananas, they needed fractions. And so that sort of brought our monkey ancestors to the rational numbers. And that's pretty good for a lot of stuff. That's pretty good for sort of things that are built out of counting and sort of comparing sort of numbers you run into when you're counting. That's sort of basic accounting. Like here you can do basic accounting, you have negative numbers, you can sort of compare different amounts of things. Sort of that's all set for that kind of operation. Our sort of monkeys started to get curious about the world around them. And sort of one monkey said, one day, sort of they held up a banana and they looked at it and they said, so what is the ratio of the circumference of this banana to its diameter? They sort of discovered pi. So So this is the circumference of the circle over its diameter. So it doesn't matter which circle you draw, this will always be the same number. And this is sort of not a number you run into if you're just concerned with counting things and sort of ratios of things. It's sort of a number you only run into if you sort of start thinking about broader ideas. You start thinking about geometry and sort of the numbers that show up in measurements of geometric objects around you. And the number pi is not a rational number. So, I mean, somehow it's not a rational number, but like sort of this description is sort of the circumference of a circle over its diameter sort of makes it clear that, well, okay, for a modern day human and a modern day monkey, sort of it makes it sort of clear that like this is something that really you should think of as existing. And so that's sort of the ontological source of real numbers, which are sort of more than just rational numbers. But you can also sort of think of sort of real numbers as obtained constructively. They're just sort of all the things you can get by approximating with rational numbers. So you could sort of, like to approximate pi, you could sort of, you could sort of draw sort of approximations of circles using sort of line segments with rational length. And then you could sort of get you could sort of do polygons with more and more sides with sort of rational length sides. You could sort of slab them on the circle and sort of that would give you a bunch of rational numbers that sort of ended up approximating pi. Okay, and so this is sort of like if you take a real analysis class, for example, or sort of a math class where you sort of work a lot with real numbers and sort of work theoretically with real numbers, sort of you'll sort of make some literal construction, mathematical construction of real numbers, sort of that formalizes this idea that there are numbers you can approximate using rational numbers. Okay, and that's sort of something we'll see sort of from a number theoretic perspective as well. Sort of, it's sort of an interesting question to ask how well certain numbers can be approximated by rationals. And then you sort of get the complex numbers. Well, here, once you have all the real numbers, you just need to sort of add in I. So I squared is equal to -1. So it's a solution to x squared plus 1. And this is sort of has nothing to do with bananas. This is just monkeys getting curious. It's sort of this sort of monkeys sort of studying equations and studying sort of questions about numbers and saying, okay, like sort of if we want to have solutions to polynomial equations, we have to have a solution to x squared plus 1, so that we have to create a number that does that. And that's sort of something mathematicians like to do too. Mathematicians and monkeys sort of like to sort of create imaginary things like that, sort of create numbers to solve problems. Okay, so anyway, these are sort of the numbers that you've probably sort of seen or are familiar with so far. And throughout the course of the class, we'll talk about sort of some different systems of numbers as well, but this is already a good start. And sort of, again, just in particular, the integers are sort of super important for us. Okay, so now what is number theory? If we know what numbers are, well, the number theory is just the study of relations between different ways to express numbers. So let me give you an example. I have the number 35. I can express that as 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 and so on. I just add 1 together 35 times. So if you count this up, I think I did it right. So that's one way to sort of express the number 35. And this is sort of how you build the natural numbers. So you sort of count them up one at a time. And this sort of only uses sort of the structure that you can sort of add together natural numbers. But there's another way to express this. Instead, you could use multiplication. So you could sort of write down 35 is equal to 7 times 5. So this is sort of the prime factorization of the number 35. And this is, instead of using sort of the additive structure where you can add numbers, this is sort of, yeah, okay, so like expressing 35, like by adding 1 together, sort of 35 times, like 1 is sort of like the atomic element. You can build every other natural number just by sort of adding 1 to itself a bunch of times. When you're sort of doing multiplication, if you want to build any natural number using multiplication, you have to use the prime numbers. And you can sort of build any natural number by multiplying enough prime numbers together. And so this is sort of how you do that for the number 35. And this is sort of really expressing a different structure on the natural numbers. Another sort of way you could think about the number 35 is you could think of it as sort of being a solution to sort of a certain equation, or sort of a number that satisfies a special property. In this case, you could think of 35, for example, as being an integer that you can get as the length of a hypotenuse on a triangle that sort of has both of its other sides, a right triangle with both its other sides having integer lengths. And another way to express that is that 35 is equal to the square root of 21 squared plus 28 squared. So this is something we sort of often do in number theories. We look for sort of interesting relations between ways that sort of integers can be expressed in terms of another, and sort of these interesting ways that sort of are tied to geometry. I mean, for most, like if you sort of just pick a random integer for this side and a random integer for this side, and you sort of compute the hypotenuse, like usually that's not going to be an integer. So it's sort of something quite special that you can get sort of 35 as an integer, as the length of a hypotenuse, where the other sides have integer lengths. Okay, and here's sort of a sort of result in the other direction. Instead, you could ask the question, can you realize 35 as the area of a right triangle where all the side lengths are rational numbers? And you can't. And it's sort of interesting to sort of ask which integers you can realize in that way. Okay, so this is just sort of an example of what I mean by sort of number theory is a study of relations between different ways to express numbers. These first three are sort of different ways to express 35. And this is sort of, this last one is saying there's some way you could try and express 35 where you would fail. Okay, so let me sort of state some important questions in number theory and just say a little bit about them. These are all sort of questions about relating different ways of expressing numbers. So one sort of basic and motivating question in number theory is, how many prime numbers are there less than 100 or less than 1,000 or less than 1,000,000? So just less than sort of some number n. Okay, and the answer is, well, the answer is that there are approximately n over the log n primes less than n. Okay, so this is something called the prime number theorem. Okay, and so this is a simple question, and the answer has a simple expression. To justify this or to like prove this is incredibly difficult. It's sort of well beyond the scope of this class. This is sort of the kind of thing you would learn in a graduate complex analysis class. So this uses sort of, even though this is a question about prime numbers, this is a question that to answer, you need tools from doing calculus. You need some advanced tools that are sort of applied to doing calculus of complex numbers, and then sort of you somehow apply this calculus to study this question. Okay, so this is sort of not an easy result, but it's true, and so we do know the answer. If you could control, so this little squiggle means approximately n over log n. So it means sort of it's not exactly that many primes less than n, just approximately that. So if you could sort of control the error, you would win $1 million. So this is controlling the error term here is, well, in a specific way, is equivalent to a famous conjecture called the Riemann hypothesis. That again, to sort of state what this means, you would have to sort of know something about complex analysis. And here I'm just saying, like, sort of just, you're just control the error just means say how good this approximation is. And there's $1 million prize if you solve this problem. Okay. So well, we're not going to talk about that in this class. That's a little bit beyond our pay grade. Here's sort of a simpler question in some sense. So when you could sort of, instead of talking about prime numbers less than a fixed number, you could ask, and this would be another perfectly good question in number theory, you could ask how many square free numbers are there less than 100, 1,000, or 1,000,000? So what I mean by square free, well, I mean like 7 times 5 is equal to 35. It's square free because it's not divisible by a square. But so 20, which is 2 squared times 5, is not square free because it's divisible by 4, 2 squared, which is a square. So that's what I mean by square free. And if I ask this question, then the answer is there's approximately, I'll probably write this down wrong. I think approximately 4 over pi squared. That sounds right. Times n, square free numbers less than n. Okay, so this is sort of a beautiful result. And this is actually sort of a little bit more accessible than the prime number theorem. So this is the kind of thing that we might talk about. And I think this will actually appear as sort of one like the more advanced exercises on a worksheet sometimes. So this uses sort of calculus, just calculus in the end. But sort of it's an advanced, it uses some advanced calculus, but in the end, just calculus. Good, and in this kind of question, so you can generalize in all sorts of ways. You can sort of pick any property of an integer or a natural number, and then sort of ask sort of like how many of numbers sort of less than a fixed number satisfy that property. Okay, so that's sort of, those are sort of some types of questions that are interesting to number theorists. Here's another one. Sort of I talked about monkeys measuring bananas earlier, and sort of, well, I claimed, like if you sort of look back up here, sort of implicitly, I was claiming that sort of pi, the ratio of the circumference of the circle over its diameter, is not a rational number. So I was using this as an example of something new you get when you pass the real numbers. But actually justifying that takes a little bit of work. So this is sort of a result of Lindemann. And sort of now sort of there's a theorem called the Lindemann-Weierstrass theorem that sort of lets you prove this kind of thing. So that lets you prove sort of pi is not just irrational, but pi is transcendent. So that means pi not only is it not a rational number, but doesn't sort of satisfy any polynomial equations with coefficients of the rational numbers. Okay, and then you can also sort of, the same theorem sort of lets you say that E, so like the base of the exponential, like the constant for compounding interest, that number is also a transcendental number. So transcendental. So E is transcendental. Sort of, you can use this to prove many other things are transcendental. This is a very beautiful area of number theory, and we'll sort of talk a little bit about some aspects of this, not sort of specifically pi and E, though this is sort of, again, sort of a difficult application of calculus. And somehow the reason this sort of falls within the realm of calculus is because you can sort of relate pi and rational numbers by taking like tangent of pi over 4 is 1, for example. So that's sort of an equation that sort of has pi in it and also has rational numbers. And then you can sort of study the tangent function using calculus, and you can sort of attack this kind of thing. So we won't sort of do that specific result, but we will discuss related ideas sort of about sort of when a number is transcendental, like when a number sort of is rational and so on. And this is sort of a very interesting, this is a very interesting realm of number theory, and definitely sort of a question number theorists are interested in. Here's another fun one. So which positive integers can be written as a sum of 2 squares? So for example, 5 is equal to 2 squared plus 1 squared. But if you try to write sort of 7 as a sum of 2 squares, you can't. So exercise for you, try to do it. You could write 7 as a sum of 4 squares. So 7 is equal to 2 squared plus 1 squared plus 1 squared plus 1 squared. Okay, so that's sort of interesting. And you can try this for other numbers and see what happens. Then sort of, okay, you can see which ones you can write as 2 squares, you see which ones you can write as 4 squares, you try and understand if there's some systematic way you can classify this. You see which ones you can write as 8 squares. Well, spoiler, it's pretty easy for 4 squares and 8 squares. It turns out sort of you can get all of them. But then sort of another interesting question is sort of in how many ways? I mean, sort of, here's one way to write 5 as a sum of 2 squares. Like, are there other ways to write 5 as a sum of 2 squares? Well, there's some sort of trivial way. Like, I could sort of make some of these, I could make one of these minus numbers. So that's sort of a trivial way to do it, but I could also sort of look for other ways. Okay. So these are sort of interesting questions. Good. And again, like, this is definitely the kind of question a number theorists like, because it's relating, I mean, somehow sort of taking an integer and asking, like, sort of, can I build this integer out of some other type of number, and sort of by adding together squares. So squares are something to do with multiplication, adding is something to do with addition. And like, the most interesting questions in number theory, sort of the most interesting questions about integers are sort of questions that sort of combine multiplication and addition in sort of some interesting way, like sort of ask how these structures interact. And so this is an example of that kind of question. Could ask, is square root of 2 a rational number? And if not, how well can I approximate it by rational numbers? So another way to think about this is like, is x squared, or does x squared minus 2 equals 0 have a solution in the rational numbers? So square root of 2 is a real number, but like, is it a rational number? Can I write square root of 2 is sort of the quotient of a over b for a, b integers? Okay, so, and again, this is, I mean, this is like, I mean, yeah, this is an interesting question. And so it's telling you something about sort of numbers that show up naturally in some way. Like, this is, so square root of 2 is the side length of a square that has area 2. And so it shows up sort of naturally in geometry, sort of, even if you just start with integers, like you're talking about an integer area, but then you have a square and you want to know like what its sides are. And that sort of gives you square root of 2. And you want to know, is that a rational number? Okay. And if it's not, like, sort of, can you approximate by rational numbers? So again, sort of, well, we'll see a bunch of interesting math related to that question in the class. Okay, and then, yeah, are there right triangles all whose sides have integer length? So look for like x squared plus y squared is equal to z squared with all x, y, z integers. So for example, I did 3, 4, 5, that gives me an example. So this is sort of the study of Pythagorean triples, this is called. And it turns out sort of you can give like a natural way to write down all possible answers to this. So you can sort of, we can find all of these, and we'll do that later in the class. If I ask the same question, but sort of I raise the exponent, so I look at sort of, I just try to solve this formula with integers, but now I sort of take the exponent to be n, where n is bigger than 2, then this has no solutions. This is Fermat's last theorem, but it wasn't proved by Fermat. So Fermat just sort of wrote down the statement, but didn't sort of justify it. This was proved by Wiles, and so Wiles is a mathematician working at Princeton. And so he wrote down a proof, and then there was a mistake, and it was corrected in joint work of Wiles and Andrew Wiles and Richard Taylor, who's one of his graduate students at the time, or I don't know at the time, but okay. Anyway, my history is not so good, but sort of in the 90s. Okay, my history is not so good because this was a while ago, but sort of, Fermat was sort of centuries ago. So this is just in the 1990s that this was proved. And they won Wiles won a Fields Medal. Or did he win a Fields Medal? Geez, I should have looked this up first. And this was probably maybe Wiles was too old to win a Fields Medal. But sort of this was a big deal. I'm sure Wiles won some prize for this. And this was sort of like, mathematics doesn't make it into news so often. This was one sort of the big times that mathematics made it into news because this resolved sort of a centuries old question. And this is sort of way beyond the scope of the class. Like this used tools that like you would have to spend you would have to do a thesis in mathematics to even start to understand the tools that go into this. Well, not to even start, but to understand the tools that go into this. Another fun question you could ask, sort of related to these other two, is you could ask if I sort of have a right triangle, all of whose sides are rational numbers, then sort of what can its like when is its area an integer? Like which integers can I get this way? So earlier I told you that 35 wasn't possible to get this way, but it turns out you can get 41 this way using this triangle. This is the congruent number problem. And so this ends up being sort of related to sort of, you can write this in terms of solving sort of certain equations in integers. This is sort of whole world of beautiful mathematics related to this problem. We might touch on just a little bit of the mathematics related to this problem at the end of the class. Okay, so that's just a sort of smattering of the kinds of things mathematicians are interested in. We'll say sort of some things towards some of these ideas, and some of these things we'll leave completely behind. And this is the only time you'll hear about them. But I wanted just to give you a flavor of the kinds of questions that number theory tackles and sort of things are interesting. Okay, and so one sort of theme is that you can easily formulate lots of simple questions, and even oftentimes like you can say the answer, like the answer has a simple form. So maybe I should say not hard answers, sort of simple answers. Maybe hard justifications. Okay. So this is sort of a theme of number theory. It's about sort of these most sort of things that are sort of at the very most primitive, most basic ideas, just counting numbers. And you because they're so simple, like you ask simple questions or lots of natural simple questions, so the answers, sometimes you can state them very simply. But because these things are so simple, like you have to work really hard to find the structure you can use to justify your answers. And so that sort of theme is true theoretically in number theory. The last thing I want to say is sort of it's also true computationally. So somehow basic computational problems in number theory are often hard. So for example, we have sort of this unique factorization theorem. So this is just sort of writing down formally that any number can be, like any natural number can be factored in exactly one way as a product of prime numbers. So I'm not going to go say it out loud. We'll spend a lot of time talking about this next week, but it's sort of written down here if you want to refer back to it. So like, okay, you can factor 91 as 7 times 13. You could factor 199,008 as 2 to the 5 times 3 squared times 691. 691 is a prime. Okay, so these are sort of examples of factorizations. And then the point I wanted to make, though, is if I just give you a number, it's very hard to find the factorization. I mean, somehow naively, the first, like, you just sort of start trying to divide it by numbers. You sort of go up for every prime and you sort of do long division and you try to do it. And if I give you a big number, that's going to take a long time. And so it turns out that even if you're to use more sophisticated algorithms, like sort of, you can't get that much better. Like it's the best way we know to factor things. Like it still takes a long time and it's hard even for a computer to do it, to factor a really big number. Even though it's sort of simple, like some of the statement is simple. Every number has a prime factorization. If I give you a number, actually finding that factorization is hard to do. Okay, but actually that's a good thing. So this is a feature, not a bug. And this is sort of the source of a lot of applications of number theory. Problems like this, where sort of there's something simple to state, but hard to do. This gives you sort of building blocks you can use, especially for cryptography. So cryptography is sort of what we use to purchase things on the internet without like telling people our credit card number. without telling people except the merchant our credit card number. And sort of somehow all cryptography schemes are sort of based on establishing a shared secret. And like the way we know to establish a shared secret using public communications are all based on problems in number theory that sort of have this feature where the sort of some part of them is very hard to solve, even though sort of it has sort of some simple theoretical explanation, like it's hard to actually compute. So this is another thing we're going to talk about a lot in this course, is sort of applications of this kind. And so we'll do sort of a couple of weeks on cryptography in particular at the end of the course. Okay, so that's an idea of what number theory is, what kind of problems are interesting to number theorists, and sort of what you can use number theory for. You'll see a little bit more on the worksheet this week, and then sort of next week, we're really sort of starting from the beginning and sort of trying to, next week, we'll sort of talk about prime factorization. And so this is sort of the step one in all of number theory. And so we'll sort of build up from there. Okay, thanks for watching the lecture. Make sure you go take the quiz, and I will see you in class on Thursday.